you on those questions. So with that, we'll introduce Professor Hamlin Jennings, the Executive Director of the Concrete Sustainability Hub at MIT. And Hamlin, if you want to go ahead and begin.
Okay, well, welcome everyone. I'm going to assume until I hear otherwise that people can hear me. My job is really one of introduction this morning. I want to set the stage for the much more interesting talks that are going to follow mine. We're a few minutes behind schedule, so I will go through these slides as efficiently as I possibly can. With the first slide, or the second slide of the two, the theme of the Industry Day held at the middle of August, just a month and a half ago, was to try to convince everyone that the program that we have here on concrete science is really one that's comprehensive and one that has a direct influence on society and the solutions that we need to obtain in order to move society forward and through the 21st century. We all know that we have some big issues with carbon dioxide, with energy, with the economy, which is certainly going to be in the forefront of the news for the next year or so. As the elections come forward, it's going to be very important. And we believe that concrete has a real impact on the quality of life. So with the next slide, I'll show you the sort of the organizational chart from a mile-high perspective. In some ways, we are divided here at MIT into two broad thrusts. One is life cycle assessment. The life cycle assessment is A, towards buildings, and B, towards pavements. And on the science side, there's three thrusts now. One is dissolution, one is precipitation, and one is the structure of concrete at the nanoscale, at the atomic scale, and we tied it. We're well into the process of tying these things together, and the glue, to some extent, that's holding us all together is industry advisory committees, which are giving us increasingly sophisticated feedback on what we're doing and how the work that's being done at MIT can impact industry. So with the next slide, I'd like to introduce the members of the hub as they stood at the end of August. You can see that this is a really very strong cross-cut of MIT with representation in the next slide from a whole number of departments, and you can see sort of a bird's-eye view sketch of the number of disciplines that are being brought to bear on this problem. It's interesting because this is a problem which, you know, there's no secret that there's other groups around the world that have worked on concrete in one form or another, but this comprehensive overview attack on the problem is really one that's now being addressed from many angles by personal enthusiasm from individuals in a number of departments. So with the next slide, I'll just give you a couple of keynote bullet items of progress that's been made on the LCA side. I think that that there are a number of reports that are online, and with the next slide, so those you can peruse, you have perused at your leisure. So with the next slide, I can show you a little bit on the LCA side. The title of this slide is really the important takeaway message. These are the most comprehensive models to date. By that, I mean that, or John Oxendorf means that both the embodied energy and the use phase have been analyzed really very comprehensively. It's the combination of these two that throws really insightful perspective on the problem. The next slide shows some of the most activities that have occurred within the hub. They are really very impressive bunch of dates. I think that this is being recorded, so I'll let you look at this in some detail, but in the interest of getting through these in a reasonable length of time, we'll go to the next slide, which shows kind of a timeline from the moment we started. This slide originally had, it sort of came up in stages, but basically quantum and molecular approach to understanding the structure and associated properties of cement, or in particular calcium silicate hydrate, have been on the science side, and best practice LCA and LCCA, the foundations for not only best practice as it exists today, but we're going to stay ahead of the curve by continuing to modify and improve this best practice. You're going to hear some pretty some of the details of how this is going to be done in the coming talks. So the next couple of slides really brings this introduction to a close. We feel that we're going to tackle the issues of the 21st century through modifying materials from where we are now to where we're going to be, and that's going to, in a holistic kind of way, bring us to a much more sustainable industry. So at the last, I think, 2 slides, I can show you a summary of where we are. We want to bind these, keep cognizant of society's needs, keep cognizant of industry's needs, which are not only being good citizens, but also keeping a good handle on the economics of any improvements that take place. And all of this is going to be generated from basic science. And then finally, a little introduction, very briefly, of the talks that are about to happen. You're going to hear snippets. This is an abbreviated version of what occurred in August, and but you're going to hear, I believe, snippets of how fly ash setting, composition, and pavement vehicle interaction are all being important components of how we move this program forward. So that's the last slide. I think it's just thank you and asking for questions, which we won't have right now.
Sure. And actually, if anyone does have questions, they can feel free to go ahead and submit them online. And you can also do that as the speakers are talking, so that when they complete their talk, we'll be ready with those questions for them. So we'll pause for just a moment to see if any questions come through, but then we'll move on to the next speaker.
I've not seen
any. Why don't we move forward with that? I'm sorry, Jennifer, did you say there was a question?
No, we've not seen any questions, but again, you'll have a little time at the very end, too, if you weren't able to submit before the next speaker comes up.
Yeah, I think I'm more or less an introductory kind of person here, okay, so great. The real meat of the matter is about to happen.
All right, so we will move on to Dr. John Oxendorf to talk about the life cycle assessment work that was completed.
Welcome, everyone. I'm thrilled to have so many of you calling in. There are a lot of colleagues from around the world and friends, and very pleased to see so many people participating today. Before I begin, I want to just briefly acknowledge that the work I'm presenting is the work of faculty from 3 departments at MIT, a number of researchers who contributed to this, and very importantly, close collaboration with industry. So there are many people who contributed to this work that I'm going to give an overview of right now. And also, on Industry Day at MIT, we presented this over about 2.5 hours, and I'm going to condense it to 15 minutes. So for much more detail, I refer you to the reports that are published on our webpage. Many of you are familiar with life cycle assessment. We are doing comprehensive accounting of the environmental impacts from their initial extraction of raw materials through transportation, design, construction, with a particular emphasis on the use phase and then disposal and end of life. And we're doing this for both buildings and pavements. Next. The field of LCA is growing in importance as industry, governments, many different sectors of society are looking to quantify their carbon footprint. And so you find companies like Coca-Cola trying to understand what the carbon content of a can of Coke is. And what this is really valuable for is not only assessing current performance, but looking up and down the supply chain and looking at where the improvements can occur. And one of the key findings of our work on concrete structures is that there are tremendous potential improvements up and down the supply chain for concrete structures, and particularly focusing on the use and performance. These are performing well now, but there's potential for improvement. Next. And LCA helps us identify these areas. This is a classic graph from McKinsey Consulting, which on the horizontal axis shows the carbon savings that are possible with a range of technologies, and on the vertical axis shows the costs associated. So there are many solutions out there to reduce carbon. Many of them are expensive, and in fact, some of the ones that are most highly touted, such as carbon capture and storage or solar PV, are quite expensive prospects. Yes, they can reduce carbon, but they're expensive. Next. Whereas in the built environment, there are a range of solutions that actually pay us money back. They save money for clients, for governments, while reducing emissions. And so our work is really focused on combining LCA with life cycle cost analysis to try to identify where the cost-effective improvements can be made. And this, for us, is really the important frontier in the next few decades in particular. Next. So the broad goals of our LCA work in the hub at MIT are to develop comprehensive methodology for LCA of buildings and pavements, to determine the carbon emissions as measured by CO2 equivalents, also known as global warming potential, for a range of concrete structures. And we've identified cost-effective opportunities for carbon reductions. And this is really the first 2 years of work, which is now completed. We're building on that going forward. Next. In the case of pavements, our system boundaries are comprehensive. We look at things including traffic delay and carbonation during the use phase, maintenance throughout the long life of a pavement. And we did a survey of other LCAs that are out there, and many of the current LCAs are missing very important components along the life cycle. Next. So the objectives of our pavements work are to develop a comprehensive methodology for performing LCA for pavements, to quantify the greenhouse gas emissions using global warming potential for a range of roadway classifications and looking at all life cycle phases, and then identifying opportunities for reductions and cost effectiveness of those. Next. This is a view of the pavement LCA model that we've developed that is more comprehensive than any other model that we've seen before, simply because we're including all of the different relevant phases within the life cycle over long-term performance of a pavement, and in particular focusing on the use phase, which plays a major role. Next. Our results, this is for 12 different roadways, FHWA roadway classifications for interstate highways down to local roads, and these show the results per centerline kilometer and centerline mile. And this allows, this quantifies what the emissions are from different aspects of the life cycle and the relative impacts of larger roads versus smaller roads. Next. And then we apply a range of different potential strategies for reducing carbon, including increased fly ash or adding an extra rehabilitation, optimizing end-of-life carbonation. And what we find is, for almost all pavements that we looked at, a suite of strategies could lead to carbon reductions on the order of 30 to 60%, which are quite substantial, and these are with existing technologies. Next. And we particularly focused on the role that MEPDG can play, a mechanistic design guide which allows for more optimal pavements and prevents over-design. And that compared to benchmark or baseline cases designed with AASHTO 93, MEPDG designs offered savings of carbon on the order of 10 to 20%. Next. And then when we compare the cost effectiveness of these different strategies, what we find is that this is similar to the McKinsey curve I showed. While there are a range of strategies for reducing carbon, there are two that jump out as the obvious winners, which both save money and save carbon. And those are increased use of supplementary cementitious materials such as fly ash in the example we looked at, and the MEPDG examples which prevent over-design are the single most cost-effective and carbon-effective strategies going forward. Next. So on the pavement side, we've identified and described transparency requirements. We've established a robust methodology to carry forward comprehensive system boundaries. We quantified emissions, identified reduction strategies, and evaluated the cost effectiveness of those. And in general, we've created a methodology that others can build upon moving forward in terms of benchmarking the current performance and future opportunities in pavements. Next. I'll switch to buildings. We've done very comprehensive and extensive studies of a range of buildings, commercial, single-family homes, multifamily residential buildings. We carry out detailed energy models and look at the full life cycle performance of these buildings, and then validate those compared to other studies and look at sensitivity of the results. Next. For the buildings, again, we're focusing on developing the methodology. We're looking at both embodied and operational phases. We're assuming a 60-year lifespan for the buildings, initial concrete mix with 10% fly ash, and then we've done a lot of work, of course, on developing the data that back up the LCAs, which is so crucial to the results, using both initial inputs from Gabby, the software we used from PE International, as well as supplementing that with our own research. Next. Our system boundaries, again, go from extraction through operation, maintenance over the life cycle, and end of life. Next. And the buildings we consider are 2,400 square foot, two-story single-family homes in both insulated concrete form construction and light frame wood, as well as 4-story multifamily and 12-story large commercial buildings. Next. These buildings are benchmark buildings that are published by the Department of Energy, so they give us standard energy and operating loads so that it makes the work more reproducible and more robust. This is the single-family construction, and we compare the climates of both Phoenix and Chicago for all the buildings considered. Next. I should say our LCA work is focusing on North America. These are examples of results for single-family homes in terms of embodied energy. The ICF has slightly higher initial embodied, this is expressed as embodied carbon, global warming potential, whereas the wood buildings have slightly lower initially. Next. But then as you consider them over the long lifetime of the building, we also emphasize the importance of the air infiltration values, looking at a range of values, and in both concrete and wood, and the importance that can play on the overall energy performance. A tight house using on the order of 30% lower energy in Chicago. Next. And when we look at the overall emissions over the life cycle due to a number of different performance features of ICF homes, we find lower annual operating energy and therefore over a 60-year lifetime lower carbon emissions than the wood. In other words, the operating emissions overcome the initially higher embodied emissions over 60 years. Next. That's for single family. I'll now move towards commercial office buildings, and when we here we compare steel and concrete next. In 12 stories, and the embodied emissions are found to be quite similar. Next slide, we find operating benefits due to higher thermal mass in the concrete building, which gives some benefits over time in terms of operating energy. Next. And when these are combined, that shows lower life cycle carbon performance of a concrete building over 60 years. Next. And in general, though we found slightly higher embodied GWP, we found lower operating carbon emissions in the concrete buildings. And we also found that the initial embodied energy was very small compared to the life cycle operating, on the order of 90% or more of the emissions come from the operating energy, and this really opened up an exciting new potential of cross-fertilization with concrete science in terms of asking what are ways we can improve the thermal performance of concrete over time, and that can dramatically improve the life cycle carbon performance of buildings, and that's a key area to focus on in the future. And also we looked at potential reductions in carbon possible through fly ash substitution and other technologies. Next. So in general, over the last 2 years, we've developed comprehensive methodology for both buildings and pavements. We've emphasized transparency and repeatability. We've benchmarked the emissions for a range of concrete structures and begun to identify what are the opportunities that are cost-effective and also deliver carbon reductions in the future, which we think is so crucial for infrastructure moving forward in this lens of both cost and environmental impact. And until now, we focus primarily on carbon performance, but there are other aspects that are important as well. So our reports are now available online, and with that, I will close. And I've gone a little bit over time, but there may still be a minute or two for questions.
Yes, and we do have some questions. The first one is, where do you see LCA going, as the LEED pilot credit is so broad it does not appear to be particularly useful for CO2 reductions through SCM use or conversion to PLC?
Yeah, I think we have to acknowledge, it's a very good question, the LEED pilot credit right now does not appear to be working. And while that is for LCA, and while on one hand that's not working particularly well, on the other hand, designers and clients are increasingly concerned about carbon footprints of their products, and so we see a lot of carbon footprinting occurring even outside of the context of LEED, and personally I think LEED is going to have to evolve and evolve pretty quickly in order to keep up with the pace of change that I see occurring in the design community, and I'm referring to things like the 2030 Challenge, which is seeking substantial carbon reductions in the decades moving forward, and in other countries and some areas where there are hard targets for carbon reductions. And so we view LCA as the only plausible method for rigorously quantifying these impacts, but the framework exactly in which it's implemented, right now I acknowledge that LEED is not working as well as it could, and so there's room for improvement there.
Okay, and then the next question we had regards, did the single-family home include a concrete basement or not?
Yes, if we look at the slides earlier, we don't have to back up, but in Chicago we included a basement where we had the diagram, and in Phoenix we did not. Thank you for backing up. One or two more slides. And so, yes, Chicago has a basement as it shows in the section, and Phoenix does not. And that was just based on what standard construction practices in each of those two locations. And so the carbon footprinting takes that into account, obviously, in terms of square footage and material quantities used.
Okay, the next question is, did you also work with other cement replacement materials such as granulated blast furnace slag?
A very good question. In the broad category of SCMs, supplementary cementitious materials, we focused on fly ash as the primary, as a primary means of doing it, but acknowledge there are many other both effective and available technologies such as slag and others. And so as of now, our reports have not focused on anything beyond fly ash, but there certainly are a suite of other technologies, and it's an example of how the work can be expanded going forward.
Okay, and the next question, what default material properties were employed in the comparison of MEPDG and AASHTO design emissions?
Yeah, those are presented in the appendix of our reports with in great detail, both in terms of mix designs and in terms of cement quantities per cubic yard and things like that. So I would refer the questioner to the reports, which are published on our webpage at the Concrete Sustainability Hub at MIT.
Okay, those are all the questions that we have for now.
Well, thank you all very much, and thank you for your interest and for following our work.
Thank you. I think there was also a question about whether the slides would be made available after the webinar, and yeah. I think if the researchers are comfortable with that, we will make those available.
Absolutely.
Okay.
Excellent.
Hello.
Thank you. So we'll now introduce Roland Paulin.
Hello. Can you hear me? Okay.
Yeah.
So good evening, everyone. I'm Roland, phoning in from Paris, France, where I'm actually spending the week. So I'll be presenting the science part of the research we do in the CSHub at MIT. So the first slide is showing what is actually the cost in terms of energy as a function of the lifetime of a building, for instance. And you can see this is an increasing function with blue sections with little kink in red. The blue part are actually the operating energy or the operation energy that basically is the heating and the cooling, while the red part of the curve is actually, I mean, and especially the one at the time zero, at the origin of time, is the embodied energy, which is the clinker production, the concrete formulation. That includes everything, actually. And also for the little kinks in red further up in time, that is the infrastructure maintenance and rehab. So if you actually sum up all those red and divide by the blue, you see that actually the embodied energy is actually a very tiny part of the operational energy. In the US, it's about 10% over the lifetime of a building. Next, please. Okay, so this is our strategy, our philosophy at MIT of tackling the problem of concrete and different phases involved, from the clinker to the set paste. And what we do is what we call the bottom-up approach. And this is both actually from experiment and modeling. In both cases, we want to have this bottom-up approach, which starts from in terms of modeling from electrons, then we go to atoms, and then at the end we go to modeling grains, and we want to connect with finite elements, those engineering methods that are actually at work already. And on the experimental side, we want to test cement from the very small scale, mechanical testing like nano-indentation, nano-scratching, for instance, and obviously connect to macro properties. So our philosophy is basically atoms from atoms to micron, to picoseconds to years, because this bottom-up approach is also in time. Next, please. Hello, next. Okay, so this is actually the menu that actually we had the other day with the researchers, and I will just first I will have three examples. The first is sorry, dealing the molecular engineering of clinkers, and the idea is obviously to reduce the energy of production related to those clinker phases. And one challenge, for instance, can we switch to belite instead of halite? And that obviously addresses the embodied energy. And in terms of chemistry behind, actually, that it has to do with dissolution rates and grinding. And as you will see, the research that we actually did at MIT for reactivity, it has to do with electrons. So we need to know where are the electrons around those atoms that are in the halide or in belite. And we see that grinding at the end of the day comes to breaking bonds in those crystals. Next, please. Okay, so this is actually as you all know, actually, halide and belite are both calcium silicate crystals. As you can see on the right, you have a snapshot of C3S here. And as you also know that those crystals are made in the kiln at quite different temperatures, high temperature for halide and low temperature for belite. And we also know that the reaction with water is fast in the case of halide and slow in the case of belite. And we want to know why, and we want also to see if we can tune those properties, so maybe to one day to switch to belite. Next. Okay, so this is a molecular simulation actually of the dissolution of halide, and at the bottom of this plot on the left you can see water molecules coming close to the surface of halide, and well, actually we found out that the water molecules, or at least the first water molecule that comes close to the surface, actually dissociate, and we have a proton penetration inside the structure, and this is a Hoping diffusion mechanism known as Grothus-like mechanism. And what is very important is that this is not the case of belite. So there is an intrinsic dissolution rate difference between halide and belite, and that obviously relates to the actual pristine original nature of those crystals. So yeah, the second consequence is that it also means that if we want to accelerating belite dissolution, we need to modify belite, and for instance by considering impurities in the crystal. Next. Okay, this is the actual measurement. So because we are not only doing simulation or calculations, we are also developing experimental methods. This is a new method which is called nano-scratching. So it's a way to probe a very important property of those crystals, which is the fracture toughness. And that obviously relates to grinding at the end of the day. And you can see that the value that is given for halide is by 4 in those units of megapascal square root of meter, while for belite is about 10. So the ratio belite over halide for the structure toughness property is roughly around 2, and which is an agreement simulation, which tells you that you need to spend that belite is actually tougher than halide and more difficult then to grind. Next slide, please. Okay, if we now convert those fracture toughnesses, Kc, we square it, we divide by E, which is a Young modulus, and then we end up with a value of the fracture energy. Okay. Now we define let's say that we take a plane of a specific surface, so that we multiply this fracture energy G with some surface specific surface area, and we end up with how much of energy, grinding energy, is spent per meter square per whatever mass of clinker. So on the plot on the right-hand side, you can see our values in those two lines actually in green. The upper one, which is for C2S, the lower one is for C3S, and in between the data that you can see are experimental values. So we are really pretty much in the ballpark of those the experimental values, comparing simulation and experiment. In this case, although we're not kind of predicting the bend of the curve, but clearly we can actually make some prediction about the grinding energy that is required to grind whatever plane. Next. Okay, so if we go for a back of the envelope calculations, as I told you, we if we want to switch, from halide to belite, we may have an energy reduction from about kind of rough calculation, be around 250 to 360 kJ per kilogram. But as I told you, if now we are playing with daylight, then the energy required to grind daylight is larger. So we have then a net grinding energy, which is, let's say, in between 180 to 360 kilojoules per kilogram. So you see, it's pretty meshed. I mean, what you get on one side, you lose it on the other side. So yes, it is possible actually to reduce the energy demand through a shift from Li to daylight, provided that we actually do something to the daylight crystal, for instance, by including impurities, and that with the idea of increasing the dissolution rate and also reduce the fracture toughness or fracture energy of daylight. Next. Okay, my second example is about setting in hardening. So what we want to understand is what is setting. So not only in terms of microtexture, but it's also related to how to predict the evolution of the mechanical properties with time. And obviously, in terms of if we are very practical, in a very practical world, for if we were to apply, we consider roadworks, that will decrease setting time to reduce or to avoid traffic delays. So it's a very practical issue there. And for the research we do in the hub, we have developed what we call statistical mechanics of grains or colloids in the case of cement, and so that we can predict the evolution of mechanical properties with time. And we have now in place a very general method that allows understanding setting from the ground of statistical physics, or very fundamental physics, in which we can actually modify temperature or interaction effects like surfactant effects and so on. Next. So this is the model. Basically what we find out is from atoms upscale, so we first design grains, so at the scale of nanos. So we have good experimental reasons, by the way, to know that the grains are on the scale of a few nanometers. And what we do actually is to do a simulation of the precipitation of those CSH grains on the left in between the clinker phases. So that's the little cartoon on the right, and you see those black dots that are clinker grains that are in between clinker phases. So we do this nano-granular model of CSH precipitation, and that relies again on statistical physics, which is for us called grand canonical Monte Carlo, which is based on knowing the grain-grain interaction, so the CSH grain interaction between two of them, or the clinker CSH interaction, for instance. And that will give us a way to predict the mechanical properties as setting occurs. So next is actually the illustration of this. We have an assembly of grains that are in those boxes with some polydispersity in terms of grain size. For instance, what's called poly10 is actually where you have a large dispersity of sizes, a large distribution of sizes, of possible sizes of CSH grain. And that model allows us to predict the mechanical properties, which is the first top plot, which is the elastic property of cement as a function of the packing fraction. And the green and yellow and gray data points are our simulations, and the small blue dots are actually the experiment as measured in the lab by experimental people using nano indentation. At the same time, we can actually use on the top of this grain-grain interaction description transition state theory that allows us to predict the evolution of mechanical properties, here the shear modulus as a function of time. And so this is the type of measurement of the simulation we can do. You see that we have two red lines for our model, and the experiment is in black, and actually the tuning, I mean the difference between the two simulation curves are actually linked with the type of how strong is the interaction between the grains. So we predict the mechanical properties from interaction between grains that are designed at the very small scales from atoms. Next. Okay, so now my last example is about the glue phase of cement, the CSH phase, and the first question is what is CSH actually in terms of, is that a collection of grains as I told you, or where are the grains? And then once we know more about the CSH, we want to know these properties like thermal mass, and obviously this addresses the operational energy, and we want also to see where, how much of aluminum we can use, how much aluminum we can dock in the CSH in the context of using slags and fly ashes, and that obviously addresses the embodied energy in my from my first actually graph dealing with buildings energy consumption. So our research, we actually will show you some new pictures of what is CSH at different scales, and see where are the grains. Then we go through heat capacities and to some aluminum substitution in CSH. And our result is that yes, we do confirm the granular nature of CSH. We recommend a large use of aluminum addition because we found that that may improve mechanical properties, and we found a link between the water content in the final CSH phase and the heat capacity then of the set paste. Next. Okay, these are three micrographs views of CSH at different scale. The first plot on the left is actually at the scale of 10 microns. You can see like CSH looks like a collection of cauliflowers stuck together. And if we actually zoom on one of those little blobs, you can see that this blob is actually made also of little grains. And if we now, so we're at the scale of 100 nanometers, this is the middle picture. And then if we move to the right to the scale of a few nanometers, okay, so we go from microns to nanometer scale, we found out that actually one of those grain in the middle plot is actually also made of little grain CSH particles that have locally some layered texture, that's what we call CSH nanoparticles. So there are grains at different scales. We, at the very early age, we didn't find any Portlandite crystals or other CSH phases. So these are very multi-scale grain. CSH is very multi-scale and very granular. Okay, next slide. Okay, now that we know about CSH granular system, we can calculate is the thermal mass as a function of the chemistry of CSH. So you have in this plot the heat capacity as a function of the water to silicon ratio, so the W over S ratio. And these are actually data from simulation of different exploring the chemistry of CSH, and we found out that the calcium over silicon ratio is actually linked to the water to silicon content. And you can see that there is a kind of not much of variation, let's say, but within like a 10% of heat capacity as a function of the water content. And so these are the blue data points. If we move to the red are for one given chemistry where we dry the system. So we have the same kind of values, and the blue shaded region on the top is actually the experimental values as we find in the literature. And obviously, the cement ratio around 2 or 1.7 or 2 is actually the normal content of water into CSH. So we found out that there is a link, a linear dependence of the heat capacity with the water content. Next slide. Okay. Okay, this is the addressing this aluminum substitutions in the context of using slags and fly ashes. On this plot, you can see the the elastic modulus of CSH as a function of the aluminum over calcium ratio. And actually, you see that this is an increasing function. And we found out that if we were to use a large amount of aluminum, which means substituting some of the weakly or defective sites, calcium sites, then we can accommodate quite a large amount of aluminum, and that actually beneficiates the structure because it does improve its mechanical properties. Okay, next slide. Okay, so that's the end for the science content of my talk. Now I just want to tell you that we are very concerned in connecting the concrete science platform of the hub to the world of the physical chemistry world, I should say. So first, we do publish every month a monthly news brief that you can actually download along with actually the LCA report on the CSHub website. We also do value a lot the visits from industry people. We had actually over the last 2 years the visit of many, many people from a few days to maybe a month or more from people coming from industry so that they get to know what we do. So we do value this kind of relationship with industry. We also set actually some relationships with NanoCem. NanoCem is a European network founded by the European Commission on cement. We had a meeting in March this year, and we are organizing a joint workshop next August in Switzerland that will be dealing with glass aging and glassy materials. So that because we think that we want, because it is a good idea to connect with glass physicists, for instance, to get to know more about CSH and cement in general. We also set some relationships with NIST, and this is our way. Basically, we are giving NIST, or we hope to give NIST the what they call the voxel. So this is the smallest grain in the lattice calculation of cement properties with the DCCTL. That's the NIST code. So we are basically giving them the initial voxel for their calculation. We also set an international research network called Multiscale Materials and a Nanoscope that includes some U.S. universities like Princeton with Paul Scherer, Berkeley with Professor Montero, Imperial College, some of the CNRS labs in 12 actually, CNRS lab in France, Labin in Bilbao in Spain. We have ETH Zurich involved in this network, and that's really a way to expose our cement research and cement in general to the large audience of the physical chemistry research in the world. And we also, obviously, we do actually produce science papers that we try to publish in first-class scientific journals. Next. Okay, this is the table that actually we designed it with the technical committee in PCA and RMCA with those technical people. We set some priorities which are on the left in red, so we can read light reactivity, aluminate reactivity, alkali effect, water and dissolution, and mechanical properties. And in blue on the say x-axis, we have what we call the CSH3 thrust, which is dissolution, setting, and hardened CSH space that I actually try to illustrate in this talk. And the shaded area in blue actually are the subjects on which we are actually acting right now, or we are doing research now. The one in white are not yet tackled. So this is what our to-do list for the next year 3 of the CSHub, at least for the CSP part of it. Next slide, please. Okay, and then you recognize this plot that was also in Hamlin Jennings' presentation. So we started first on the left with the bottom green box. For us, looking at existing materials, and then, for instance, through the accommodation of aluminum in the structure, we try to move to new materials. And as we move to new materials, we can actually go vertical now and consider new designs and new structures. And obviously now we are on the top right box of this plot. And obviously that in the way towards sustainability with new materials enabling new structures. And I think this is my last slide. Thank you.
Okay, we do have some questions.
Okay.
All right, the first is, and I apologize for the feedback, for manipulating CSH examples, what form is the aluminum?
Okay, actually, we found out that there are two ways to accommodate aluminum in CSH. The first is very general, I mean common to any stones or any minerals actually in nature, which is substituting silicon sites. But if you do this, so that first, I mean, is not giving you a lot of aluminum, maybe 10, 15%, but the idea is that we are reproducing the NMR, solid-state NMR data available in the literature if we are to consider calcium substitution. So we're substituting some of the interlayer calcium, because CSH is a layered material, some of the interlayer calcium by, for instance, 3 of them by 2 aluminum, so to remain neutral. And with this, actually, we find out that the aluminum diffuses, okay, and so that we found the lacune in the silicate chains. So there is a healing procedure or healing process of the silicate chains, and not only it goes towards lengthening the silicate chains in the CSH, but it goes also to cross-link 2 layers together. So this is why with this calcium substitution for aluminum, if we put a lot of aluminum, we improve the mechanical properties of CSH.
Okay, and related to that, doesn't aluminum production take a lot of energy?
Oh, sure. I mean, the thing for us is slags and fly ashes are subproducts or byproducts of the steel industry. So, I mean, the idea is to use those raw materials as the new cementitious to produce some more CSH or stiffer CSH. And obviously, these slags and fly ashes are coming from a part of the industry that obviously uses a lot of energy, for sure. But the idea is to use those byproducts or subproducts of the steel industry into CSH.
Okay, the next question is, could you please shed more light on the slide with the curve where you compared the CSH combinatorial model with the varying water-silica ratio to energy?
Okay, so where's the one? I think we need to back up a little bit with energy. That's not the one, because there's no water there, just maybe the one before. Yeah, that one, I guess. Oh, that is the heat capacity, yes, okay. So I'll come back now. That's the one. The heat capacity is a function of the water to silicon ratio. So the idea is the following, is that as we move towards large values of calcium over silicon ratio, in fact, we have less silica in the structure, okay? In fact, this is a way to accommodate more water molecules. So there is a linear, actually, relation between the water content and the calcium over silicon ratio. Now, turning to the heat capacity as a function of water, this is why we actually have also this linear plot in this case. And so the blue line are for natural, let's say exploring all the possible chemistries. The blue points are for exploring all the chemistries of CSH as a function of silver S ends of different water content. And the red points are taking the most common silver S, which is 1.7. Okay, that has also 1.7 for the value for the water towards silicon. And as we go towards on the left, on the red points, we are actually drying the system out. So we're taking the water out. And you see that we have a linear dependence again of the heat capacity as a function of water. So this is why we are stating that the heat capacity of cement is actually linked to the amount of water in CSH. Now, to tell you the whole story, is that it is very hard to go to dry the system completely in CSH. We found that there are some part of the water that is not, that is very difficult to take out of the system just because it is very chemically bonded to CSH. So these are, by the way, simulation results.
Okay, there's a follow-up question with respect to what SCMs contain high aluminum?
SCM. So aluminum, I guess, next slide. Okay. I don't get the question. STM? What is STM?
Supplementary cementitious materials.
Oh, okay. I mean, the idea is that if we are to improve the mechanical properties of cement, we need to substitute the calcium side, and to do so, we need to first substitute the silicon side. So it means that we go first for the silicon and then the calcium. This is why we need to go to actually consider a lot of substitutions of aluminum in the structure. So the idea is to put a lot of aluminum rather than a few.
Okay, and then another question: what are the implications of fly ash classes, particularly Class C and F?
Yeah, I think the implication, for us, the fly ashes per se, we need to basically extend our reactivity study that we did for BLite and LI towards this class of materials, those fly ashes, right? Because I know that one class is more reactive than the other one, which is reactive in terms of being able to produce, to react with water, for instance. And clearly, this is not understood yet, and we are starting this research now. We have a new postdoc coming in the hub to actually tackle this reactivity, surface reactivity of fly ashes, for instance.
Is the fly ash slag added to the raw materials in clinker manufacture to gain the required substitution?
I don't know the amount, the natural amount of cement, of aluminum in the structure. I don't have the numbers with me, but the idea is maybe to go beyond that point, so that maybe few percent, and maybe we can go to like 20, 25%, 30% maybe. That will require also to do some nano indentation on those controlled samples, for instance.
Okay, that's the rest of the questions. Thank you very much.
Okay, pleasure.
Okay. Kristen, you are now unmuted.
Okay, great.
We will be able to connect.
Yes, we can hear you.
Okay, I'll just pick up my speakerphone. Okay, so thank you, and I want to echo the previous comments, appreciating the time that you guys have spent hearing more about what we're doing and allowing us to receive your input. So what I'll be doing is wrapping up the discussion we've had so far and figuring out how we can move forward together. And we chose 2030 as a target date for some reasons that may seem obvious to you on the architectural side, but also as a 20-year out goal for ideas and projects that will span and move the industry forward over a foreseeable research lifetime. So I'll be presenting to you a couple of areas. So what we're going to cover in this last presentation here, I thought was best for us to take a step back and say, where were we when the hub first started? Where are we now as of literally today, but when we gave this presentation in August, where were we by that industry day? And then where are we going by 2030? And you've heard hints of these ideas on the LCA side and on the CSP side, but thinking forward even more. So in August 2009, let's keep in mind that there was no hub. It didn't exist at that time. It was a conversation that we were having among folks in industry, folks in government, and folks at MIT. And at that time, the industries were confronting a lot of pressures on the economy to actually find new approaches and deal with the same economic difficulties that academia was dealing with. And the carbon cost models were being hotly debated up in Europe and affecting a lot of those decisions. On the U.S. side, not the European side, our physical infrastructure was being given dismal ratings by our own civil engineers and the National Academy. So there were a lot of opportunities, but there were also a lot of risks. The next slide, if we look at where we are 1 year later, so now in August 2010, the CSHub existed, and it included faculty from 5 departments and 2 different schools with 20 graduate students and postdocs who are conducting research in the areas that you have heard about today. And we were able to hold our first industry day, formally engage the industry who were sponsoring this so they could learn more about our methods, our approaches, and our ideas, and that we could get input from them. So this is the year that we started to forge those key partnerships to exchange data, exchange ideas, and also exchange people. Okay, so in the next slide, now we're in August 2011, and it's really remarkable to think where we've come in those 2 short years. So we hosted our second industry day. We had hundreds of colleagues from other universities, from the industries that were sponsoring our research, as well as the ancillary industries that were just wanting to see what was on the horizon, and also the government. So we were really putting forth our best ideas, and we were getting their best constructive criticism and input and enthusiasm. And we were beginning to identify together clear opportunities for moving forward, both on the design of new structures as well as on the design and processing of new materials. I think that's really, when you think about how quickly this has evolved, a rapid accomplishment. So now I'll just give you the highlights to summarize what we discussed in terms of the science related to the CSHub. So on the next slide, first, just to recap where we were on the key findings from the life cycle analysis thrust area of our team. In the context of buildings, we've learned a few things, and I would say that the 2 major things that we've learned over the course of 2 years of study is that the majority of the emissions, the equivalent carbon dioxide emissions, greenhouse gas emissions, are due to the operating energy of the buildings, the operating phase, and not the embodied phase of the raw materials. And a corollary to that is that identifying key properties that can actually change that operating cost have been one important outcome of the LCA. For example, the thermal mass of those concrete buildings is a cumulative effect in terms of energy savings and sustainability. So if we think about now what we've learned in buildings, that's one approach, but the LCA has also looked at the concrete pavements. There, the key accomplishments, as we see them, were establishing the first benchmarks for typical structures so that we could compare and contrast an interstate from a local roadway, see the ways that they were the same in terms of how choices in concrete supply and processing made a difference, and also see the way that they were in sharp contrast. Importantly, we've also identified the potential for significant reductions in the global warming potential. And these aren't reductions that are based on a whole new market model or a whole new set of materials. These are actually rather incremental changes that the industry could implement now that could offer cost-effective but also very significant reductions in greenhouse gas emissions and global warming. So one of these accomplishments and contributions from the LCA side is to actually help us to articulate to the wider community, not just within the industry, but to the larger public, what the cost, the energy cost of structures such as buildings is. And for example, in a car, we know we established the miles per gallon as a measure of fuel efficiency, and now we know for the buildings the best way to articulate that and compare choices is this global warming potential, or GWP. So this is really the energy cost, just like the fuel efficiency of your car. And you can see this compared here in the context of the roadways. For example, you can see that the highest cost is for building interstates. Among the lowest cost is local roads. But more importantly, you can see how much of this comes from the cement production, how much of this comes from the traffic delay, how much of this comes from the mining of aggregates. So you can make choices on how to bring down this GWP, or this environmental cost of building roadways, because the information now is not just validated and the methodology is not just transparent, but it's also connected to the science.
Excuse me for just one moment. I'm sorry. I just wanted to let the attendees know, for anyone who has raised their hand through the system, I would encourage you to instead submit a question, because it's difficult to answer raised hands, but just submit your question through the questions section on the right-hand menu. I'm sorry to interrupt. Go ahead.
Okay, thanks, Joy. So if we look at the next slide, here's an example of not just do we know how to quantify the energetic cost in terms of greenhouse gas emissions through this GWP, but we can also compare different choices of how to bring that down. So, for example, if you look at this graph, which John already discussed with you, you can see that each of the colors of the bars under, let's say, the local road is the baseline cost of building a local road, and then different choices we can make to bring down the global warming potential of the local road, adding more fly ash, adding white aggregate, combination of existing strategies. And what's exciting is that these choices are real and these choices are well within reach of the industry to implement, but they can offer a plausible and very credible, approximately up to 60% reduction in the energy burden of creating, for example, a local road. And it's not really in our purview to actually implement combinations of these strategies, but it's that rigorous analysis where you can go back and make your own choices of how to move the industry forward based on these data being validated and transparent in the way that they have been. Okay, so next slide. On the CSP side, so our concrete science platform side, there are several key findings. I just wanted to highlight a couple that I think are most intuitive. So starting with the very beginning of creating cement, paste, and concrete, we've thought quite a bit about clinker reactivity. For example, those of you who work on this side of the house know that there's a gross difference in the reactivity and the dissolution and the precipitation and the kinetics of forming cement paste using clinker that is rich in alite versus baelite. And these are different crystal structures. Through the atomistic models, we now understand why, not just that they differ, which has been empirically known for a long time, but why, and then how we can modify that by introducing substitutional elements into the clinker, which is already done in practice, but not with any quantitative understanding as to why, and really make rigorous predictions of this, and then in partnership with the LCA side of our hub, be able to say, well, is that worth it? If we were able to make and engineer a new clinker, will that bring down the GWP of the roadway in a way that we can argue is a substantial advance? So this gives quantitative tools to guide your decision making. On the clinker grinding side, which is also a very energy-intensive part of the process, you can see that we've come, oops, sorry, we're still on that slide. You can see that that is something that is empirically known, that it takes a lot of energy to grind a clinker, but now we actually have a way to measure that experimentally and then see, well, how do substitutional changes in the clinker that might make it reactive make it easier or less easy to actually then achieve the grinding step. So there'll be energetic trade-offs, and we're now in a position to not just predict them through computation, but validate them through experiments that have been developed specifically within the hub. Okay, so next slide, moving from the processing onto the properties. We're concerned with various levels of properties, and Professor Palant gave you a nice overview of that. One of the areas that we're interested in is understanding how to predict the precipitation of that CSH, or calcium silicate hydrate phase, because that's one of the most difficult aspects of cement paste formation and the resulting concrete product to predict. So we're actually developing new ways to understand and predict precipitation at the atomistic scale, and then we're going to form hypotheses. We've actually begun to form quite a few hypotheses in terms of how is this affected by the calcium to silicon ratio, how is this affected by pH, by temperature, by choice of clinker. And again, a very strong motivation on the concrete science platform side is not just to make computational predictions, which in isolation are not useful to industry other than thought experiments, but to validate them with experiments. So the black and white figures you see on the right are experiments that are very novel and were developed for other purposes related to drug discovery, but we've actually adapted them within the hub to study this precipitation of this key phase within the cement paste. And that back and forth between the models, which are able to predict this precipitation and setting over seconds to hours to days to months, is now being directly validated within the experimental part of the concrete science platform. Okay, next slide, please. Okay, so that's the science, and you've heard that. I just wanted to recap the highlights rather than and bring you out of the details, but there's also quite a focus that we have in the Hub on society. So if we move to the next slide, I'll just highlight for you that one of the important roles that the Hub serves, next, besides just doing research, which you also do within your industries, is to really educate and create. No, go back, please. There might be a little time lag between what you're doing and what I can see. Okay, so we're creating the next generation of researchers, which you may choose to hire into your companies, who may choose to stay in academia, but they'll be moving this forward. And there's really an amazing array of researchers at the undergraduate, graduate, and postdoctoral level who are extremely eager to conduct this research. They see that it clearly identifies with their world. They resonate with the idea of sustainability. And once they're engaged in the research, whether it's on the LCA side or the CSP side, they find this a fascinating topic where they want to spend the majority of their research time. And we consider that not surprising because the faculty members also find this a rich and interesting research area, but very gratifying because this is a mature material. We are competing for these top students and postdocs with faculty who are studying, the next drug to cure cancer or the next solar cell design. So the fact that there's a large number of people who are streaming into MIT to work on this problem, I think bodes very well for the future of the industry. Okay, next slide. We also within the Hub do quite a bit of outreach, and here's just a few examples of that where our graduate students are conducting demos for the wider community that are being published in local papers. MIT celebrated its 150th anniversary this past spring, and we had several activities for the Massachusetts community who came out in terms of learning what the scientific issues and challenges are, what the environmental opportunities are, and even how to make cement so they actually understand more what it is as a material, what it means to make cement paste and concrete. And then we also do quite a bit of outreach and interaction with the government. So for example, this is a photograph of me in the black and Senator Kay Bailey Hutchinson of Texas in red, where we visit and we share our perspective, not as advocates of the cement and concrete industries, but as advocates of using science to make public policy decisions and what we're doing within the Hub to advance that way of thinking. Okay, next slide. Okay, and then finally just pointing forward towards solutions. So with the science and with these societal opportunities in hand, where do we go from here in the next 20 years? Next. So this challenge that we set for ourselves to figure out where we'd like to plot our trajectory up to 2030, we can really think about in a few different areas. And again, we bring back this graph of greener structures and greener materials to guide our thinking. But our goal is to move to new materials and to new structures by using the platforms and the methods that you've seen discussed today. So we're interested in identifying ways that will truly change the properties of cement, paste, and concrete. We're also interested in identifying, in partnership with you, the structures that are taking best advantage of the properties that the current materials have and the new materials will have in spades. And then how will these changes impact the environment and the economy? We're in a unique position to think about this in ways that might be different from industry because the perspective is different, but also to articulate that and influence the education that brings the next generations of researchers and policy decision makers along the way with us in terms of how to connect science and engineering to architecture and also to policy. So next slide. So in terms of the new materials, Roland touched on this a bit, but I'll emphasize it here. We are really identifying the ways to scientifically, with predictive capabilities, introduce new substitutional elements within, for example, the calcium silicate hydrate phase itself. So you can add filler, you can add fly ash, for example, but you can also think about how can I change the final composition of the CSH, engineer ways to do that. And then what will that do to the stiffness, the strength, the creep, the shrinkage of cement paste, of the final concrete, and how might that enable new applications for pavements as well as residential buildings. Next slide. We're also interested not just in new materials, but as I said, new structures. So two of the areas that we're actively engaged in discussion with others and also work within the hub is to think about how to change the building design itself. For example, introducing a vasculature, just like we have in our bodies, but within a building to have cooling that really takes advantage of the thermal properties of cement and concrete in their best possible light. This involves a lot of very intense discussion and coordination with people who set building codes, with architects who design buildings, with the other materials that are always going to be integrated into roadways and into residential structures. But by changing the design to make best use of the existing materials and best use of the future new materials, we think this is the wave of the future in terms of introducing sustainability into the infrastructure. Next slide. So in summary, what we've been able to accomplish in the past few years has been focused on current structures and current materials. And there LCA has played a key role in identifying the opportunities moving forward that can change the equation, that can bring down, for example, the global warming potential of our roadways. We've also started to identify ways to change structures using the current materials. For example, using the thermal properties of concrete, such as the thermal mass, to the best possible advantage, which parts of the building, and so forth. We're moving towards identifying ways to use new materials within current structures, and I think you see that in the context of the pavement and the pavement-vehicle interaction, so that we can impact the fuel consumption of cars that are driving on our current roadways by bringing in new materials and new material processing that will, for example, increase the stiffness of the final concrete structure. And then finally, where we're going moving forward will always be the identification of the best pairing of new structures and new materials, and really having the structural demands guide the materials development at the scientific level, as well as the new material capabilities inform better and smarter and heretofore impossible design of structures. So the Concrete Science Platform is really providing the potential to bring down the carbon dioxide burden and even introduce new functionality into the cement and the concrete products. But we need to do that in the context of always keeping an eye on the life cycle and life cycle cost analysis. Next. So our challenge is really to realize sustainability, and we're going to do that by first impacting the science. And so moving forward, we're increasingly focused on integrating what we are doing on the life cycle cost analysis side and what we're doing on the Concrete Science Platform side. So to get that back and forth going, because our tools are in place, our methods are there, our team is now very, very competent in understanding the science and how to interface with the various industries. So we need to get the results, making sure they're talking back and forth to each other and enabling new solutions. On the societal front, we're training the next generation engineers. We are, to the extent that we can, influencing the ability of policymakers to understand the science and the technology that we and the industry is developing. And on the solution side, the closer we partner with you to develop new materials, new applications, new structures, and even the motivation and the scientific underpinning for new policies, that's where we're going to be successful. So for us, success 20 years out will be a new generation of researchers and policymakers that say, of course, we would consider using cement and concrete for the right parts of the right buildings because our goal is sustainable infrastructure. Of course, we would think about changing our water distribution methods or our electricity grid to use these materials in their best light. And so that's what we'd like to see moving forward, and that starts with increasing interactions with folks like you.
We do have several questions.
Okay, so thank you for your, sorry, I was just waiting for that last slide. So definitely welcome your input. I'm happy to take those questions, so thank you.
Okay, and also too, if the other presenters are muted, so if you want me to unmute someone else, please let me know.
Sure.
The first question is, what practical use is being made of the research done to date?
So that's okay. So I think if I could paraphrase the question and say, are there new cement and concrete products going out because of the research we've done so far, or are there new structures or standards being designed and implemented out in the public? I would say that the answer for that is it's too soon to realize that. We've been building up the team and the capabilities. But where we know we're going forward in terms of what we're developing is that the models that have been developed within, for example, the LCA side are to the point, established to the point where we're actively engaging industry so that they can become tools that are used within the industry. There have been several discussions along those veins. And we have many visitors from the various sponsor companies working within ready-mix concrete, aggregate industries, PCA. So those of you who are contributing to the sponsorship are visiting us regularly, and we are brainstorming on, for example, how to commercialize the fact that we can change the ability of water to move in and out of cement to reduce shrinkage. So these are longer-term goals and longer-term conversations, but they're ones that we're having on a near weekly basis with industry. So I would anticipate that within certainly within the next 3 to 5 years, you will start to see some of these scientific methodologies and predictions that have been experimentally validated in-house, creating new product streams, creating new ideas and internal ways of doing research within the industry. But there's nothing for sale, whether it's on the LCA side or on the materials development side at this point.
Okay, the next question is, what is meant by end-of-life carbonation?
Okay, so that's a technical point that I'd like to defer to John. So if you don't mind bringing John Oxendorf back on, he can articulate that much better.
All right. 1 second. John, you are unmuted.
Yes, thank you. So any concrete over its lifetime continues to reabsorb carbon. It carbonates, and that occurs at different rates depending on it's essentially proportional to surface area exposed. And so the idea here is that before concrete, if it's taken out, if it's demolished, before it's reincorporated into a new project, which is often the case where it may be used as fill or even aggregate in a new project, that it be left exposed to the atmosphere to reabsorb carbon when a larger percentage of its surface area is exposed. So that's a very short answer, but basically it's a strategy for removing carbon from the atmosphere by accelerating a natural process that occurs as concrete carbonates throughout its lifetime.
Okay, the next question, and hopefully I say this correctly, Mg++ in solution is a strong cosmotroph. Have you therefore considered adding reactive MgO to your formulations to enhance the proton-wrenching dissolution of high B-like cements in accordance with our patents? This mechanism also works with slag. Should I unmute Roland for that?
You can, and also I can answer this because it's a straightforward answer. But can you repeat the end of it? There was some interference there.
Okay. Yes. The Mg++ in solution is a strong cosmotroph. Have you therefore considered adding reactive MgO to your formulations to enhance the proton-wrenching dissolution of high B-like cements in accordance with our patents? This mechanism also works with slag.
Okay, so I think that you can unmute Roland in case he wants to add anything specific, but experimentally we have not added MgO. Computationally, however, we have systematically considered Mg and other divalent cations that could be added and how they will change the structure as it relates to dissolution and also to the mechanical properties of the calcium silicate hydrate. That was part of a more exhaustive study where we considered many, many options for different ions. So we are considering that computationally. We haven't identified results that have motivated us to systematically do that experimentally, and I don't know which patents are being referred to here, but it's certainly something we would be willing to engage in partnership with those who are interested in exploring a specific composition. I don't know, Roland, would you like to add anything further?
Well, yeah, I mean, just to say that, yes, Christine is absolutely right. I mean, we have tried, I mean, computationally speaking, a lot of things like we've been to Mercury, for instance, also. And the idea is that we are exploring, I mean, many different ways to do substitutions and to see how it impacts the mechanical properties for CSH, or if we turn to clinker phases, how it impacts the solution. And we have a full story from Professor Grossman and his crew of people saying, showing what are the good impurities to destabilize delight, for instance.
Okay, I'm going to remute you, but I'll unmute you if I need to for any other questions. Okay, the next question is, has the Concrete Sustainability Hub given consideration to buried structures such as storm sewers?
So that's a very interesting question, and in fact we have, although we haven't really articulated the use of those various structures. So on the concrete science platform side, we're very interested in the environment that surrounds the cement paste and the concrete and influencing how the properties and the structure change and evolve over time. So for example, cement and concrete structures that are going to be surrounded by water, if they're used for example, reservoirs in a water setting or beneath the water table, that's something we have considered explicitly and what that does to the evolution of the property. We have not considered that type of structure within the LCA side because the original purview and scope was to focus on pavements and buildings. But as we move forward, if there's strong motivation to look at particular structures, that's input that we would love to have, because from a scientific point of view, these are equally interesting targets for us, and industry input into the most interesting targets from an industrial perspective is a conversation we're happy to have.
Okay, the next question is, what is the effect on or consideration of corrosion resistance of reinforcement?
So that's a very interesting topic, and we have explicitly discussed and chatted about investigating that issue with particular partners. That is beyond the scope of what we are right now considering for the concrete science platform side. And the reason for that is we focused our efforts right now on predictive capabilities related to the genesis of concrete. So how does cement paste and concrete form develop, and what are the resulting properties? So we haven't added the complexity yet of composite structures that are obviously used quite a bit in engineering practice related to steel reinforcement and then the ensuing corrosion. That is something that's within the purview of the capabilities we've developed. It's an additional complexity. It would take an additional involvement, but it is arguably an important part of the implementation of a lot of our predicted solutions. So the way that we've been working to engage industrial partners is if there's a specific company that's within the PCA that where the problems that they're interested in studying fall outside of the methodologies and the results that we're developing within this charter, as we've discussed to you today, those companies come and visit. We discuss that. Are there opportunities where we could move forward together? Don't distract us from the mission that we're doing for the hub, absolutely, but can be complementary extensions of that. So if you are interested in discussing those one-on-one, that's why we have these open doors to industry visits, so that we can initiate and sustain those interactions on problems that are ancillary but still quite important.
Roland, you wanted to add something?
Yeah, I mean, just to say, yes, I mean, this is not yet, I mean, we're not yet running on this aspect of things, but clearly, if I were to rephrase that thing, that question in terms of our science that we do, that would be the interface problem. Yes, we are interested in the steel same CSH interface. For instance, we are interested in the grain, I mean, silica grains or aggregate interface. So this is a very broad range of very interesting questions that we may consider in the future.
Okay. All right. The next question is, Does your program examine pervious concrete in the scheme of energy savings? If so, what quantifiable energy advantages does it provide?
I think that that is probably a question best addressed by John in terms of the assumptions.
John, you should still be on mute.
Yes, no, so the, as of right now, our focus is primarily on building scale and does not include other pavement structures like parking lots adjacent to buildings. And so as of right now, it's not incorporated into the building performance model, but is something that could and should be added and can have an important impact both in terms of water performance over the life cycle, but also urban heat island effect, which can influence building energy use. So the short answer is right now it is not incorporated, but there are many potential impacts that it could have.
Okay. The next question is, why did you choose 60-year life cycle for LCA? Concrete buildings properly built can last much longer than this.
Again, that should go directly to John.
Yep, fine. Good question. There are examples of, there have been some studies that looked at buildings that were torn down and looked at the reasons for demolition and found many buildings are being torn down after 40 to 50 years, and reason for demolition is not necessarily lack of structural capacity or degradation of the building, but simply functional obsolescence. And so so we chose 60 years in part because that's what, for example, the LEED credit uses 60 years, and that is a fairly standard time period in building life cycle. Some people use 40 years, some people use 50. But I think the other important thing to add is that it can be part of the argument for increasing sustainability of infrastructure is building longer, but we do have to acknowledge the need for flexibility throughout the lifetime of buildings and infrastructure. We often find buildings being retrofitted over time. So that's a brief answer, but I think it gives you a sense that we looked at a range of different life cycles. And I will say that for the LCA results generally in a period of 40 years to 80 years, you get similar results. In other words, that it doesn't radically change the overall conclusions if you're in that kind of window. But another good question. Thank you.
Okay, the next question. Further to the structure of storm sewers and considering possible corrosion of the concrete material, can the science of changing mechanical properties be used to make concrete more durable and resistant to issues like acid attack?
So the answer to that is a straightforward one. Certainly the answer is yes. And the reason why we can say that so confidently is not because we know how to specifically, for example, increase the acid durability of concrete by a factor of 10 today, but through research that we've done on many other materials with comparable complexity, polymer nanocomposites, certain ceramics that are used in the energy industry, even biological materials. We know how to attack these problems from both a computational and experimental point of view. In fact, working on how to make materials mechanically durable in so-called extreme environments of, for example, high acidity, low and high temperatures is something that is become quite an area of expertise for MIT, and it's an area that we've been working on in the context of the cement and concrete research quite actively. So we have not currently planned to approach this specific problem, meaning the high levels of acidity that would come from aqueous corrosion of metal alloys. But it's certainly something that those of us on the team who work on many other types of materials besides cement and concrete are capable of doing if there were sufficient interest and moving of our priorities in that direction. But again, for those of you with those ideas and specific interests that aren't about just the genesis of concrete and just the use of concrete in isolation, but also concrete in more complex systems. It's very important, and we certainly welcome you to come by and discuss those in a bit more detail.
Okay, there are a couple more questions. First, I do want to answer a question that somebody again asked if the presentation will be available. We are recording this webinar. We will make that available, and I believe Julie said earlier we will also make the slides available for download as well. Give us a couple of days to put everything together and get it up on the websites, but they will be made available. The next question is, have you tried adding red mud with fly ash or brown GBFS in compositions? I found red mud or alumina, both found in abundance, improve the physical properties of cements and mentioned some detail of this in our early publications. You have provided additional insight as to why this may be so.
So we have not done that, but it's, I think that that's a very important example of the fact that many of you have tried experimentally iterations that we have not, because we're focused right now on the predictive understanding and the general principles that help us understand what we see in the lab and in practice out in the field, but we don't quite understand. So the fact that you can see some of the arguments that we're making for why and how cement and concrete form and reflect that back to the things that you've tried and we have not, and you understand them better because of that, that's one of our benchmarks for success. But no, we have not tried that particular modification because we're still focused on, right now, the ordinary Portland cement and understanding the evolution of that product with the minimum of additives.
Okay, that actually was our last question. So great. Well, thank you, everyone, for your participation.
Thank you.
Yeah, and again, this will be on the website hopefully in the next 48 hours or so. Thank you, everyone.
Great. Thank you so much.
Thank you.